Hiya! So in this video, we're going to be looking at basically an arbitrary continuous distribution. So we'll look at two kind of examples of these. It might be split into two videos, but we'll kind of see where things go from here and kind of go from there like a little bit at a time. So let's first look at one example. So the first example we're going to look at is a bacterial colony. So we'll start off. So we assume we have some bacterial colony which appears uniformly distributed. So at first you might be like, oh, uniform. This must be the continuous uniform distribution. But no, you got to kind of always read the whole thing. It's uniformly distributed at random on a circular plate of radius 1. So what this is saying is I have some circular plate. Here the radius is equal to 1. This is 1. And it's uniformly distributed on this. And I don't actually know what my function is yet, right? I didn't say it's a continuous uniform distribution. I just said it's uniformly distributed on this plate. So in other words, a bacteria could be anywhere on this plate. That's what I'm saying here. We're letting R be the random variable which represents, so I'm already telling you what my random variable is, the distance from the center of the plate. So in other words, if I were to look at some points, so if I find some bacteria here, this is going to be my R here. And so the question is, well, what is the probability density? What is the probability from A to B, the expected value, and also the variance? So basically kind of give me all the basic information that we need. So first, let's kind of break this down. So how do we figure this out? First, before everything, we need to figure out the probability density. So this is the most important thing, probability density. And this is where I'm using your tools from calculus and integration to kind of do things. So one of the big things I hope your previous instructors looked at in integration class was, I think you probably saw like rate of change problems or like integration problems where you actually had to solve, like look at what an integral, you had to create the integral kind of from scratch using some word problem. And so this is basically what we're doing. So here, if I take some radius r, well, what we're going to do is, well, okay, we want to look at all the radius, all the, we want to see all the bacteria that are r distance. Well, what's this r distance? That's going to just be all of, maybe I should use a different color. It's going to be all of this thing here. Well, obviously, I can't really get the area of this, right? Because there's no area formula. I need some depth, right? And so the thing we normally do here is we add some small dr, right? So we add some small radius, and we take a second band, and we take this area here. And we look at this, right? And we integrate over our formula. So what is our area here? And this is basically going to give us our probability density. So in other words, what we have is, let's see. So we have the green circle. So the green circle is going to give me, what's the area? It's pi r squared, right? So it's pi r squared. And r is, we'll use little r. So r is equal to r plus dr squared. And we want to subtract out the blue circle. So we want to take away the blue part. So this is pi times r squared. But we also want to see this as a proportion of the entire thing, right? So we want to see this whole proportion. This is just going to give us an area, but it's not going to give us a proportion. So really we want to divide by the sample space. And in the sample space in this case, is just pi r squared, which is the whole circle. And since we have a unit circle, in other words, the radius is 1, we have pi 1 squared here. So let's multiply this out. Here we end up getting pi. So here we can kind of see all the pi's cancel. So I guess I don't need more pi's. And I have a 1 on the bottom, so really I only care about the thing on top. So I have r squared plus 2r dr plus dr squared minus r squared. So here we really get 2r dr plus dr squared. Now since dr, remember, is infinitesimally small, well, dr squared is even more small. So we can basically just ignore this part, right? This part means absolutely nothing for us. So we just ignore it because it's too small. Too small. And so now we should see something that looks like what should be our probability density. So basically what we have is our probability density of r. Well, this is just going to be 2r because we haven't taken the integral yet. 2r. Now this, we have to figure out what the intervals are. Well, it's going to go from 0 all the way to the edge, right? So in other words, I go from 0 all the way, I guess this is r now, to 1. And it's going to be 0 otherwise. So we just let it be 0 everywhere else. Well, so this basically, that's our probability density. So from here, everything else becomes super easy. So the probability is just a less than or equal to, r less than or equal to b. This is the integral from a to b of, fr r dr. So here basically, what we end up having is, so here's a little complication in that you have to figure out where these bounds are. So if a or b are outside of 0 and 1, this is going to be a little more complicated. So if we have 0, a, b, 1, then we get, I guess I should put this underneath. Oh, bananas. I can't because I did that. So we have to break this up into little portions. So if, do I have room underneath? No, I don't. So if A and B are contained in 0, 1, and we'll say C and D are not in 0, 1, where we have A is less than B and C is less than D. I'll kind of do all of these at one point. Then we have the following. So this gives me, so A to B, I would have to do 2r dr, and this is not too hard, right? So it's 2r squared over 2 from A to B. So this is b squared minus a squared. If I have C to B to here, well, from C to 0, I have nothing. So this is just 0 to B, f 2r dr. So it's basically r squared from 0 to b, so it's just b squared. If I were to do, so this is my 4 options. If I were to do a to d, you should see this is kind of a very similar thing, fr dr. But here I would have it a to 1 to r dr. So it's r squared from a to 1. So I get 1 minus a squared. And then finally, if I were to do c to d, fr r dr, this is just 0 to 1, 2r dr, which is just r squared from 0 to 1, so it's just r squared, 1 squared, so it's just 1. It's the whole area, right? So that's the probability. I don't have enough room, so I'm going to just do expected value and stuff underneath. So here we're just going to look at E of r. This is just going to be from 0 to 1 because everything else is 0, so I don't care about it. R times 2r, which is our function, dr. So this is just 2 times r cubed over 3 from 0 to 1. So here you should see easily that this is 2/3. So our expected value is 2/3. And ER squared, 0, 1 is r squared times 2r dr. So here we get 2 times r4 over 4 from 0 to 1. So we just get 1/2. So this 1/2 is basically telling me that the variance of r, which is e r squared minus e of r squared, is 1/2 minus 2/3 square, which is 1/2 minus 4/9. So let me convert. This is 9 over 18. This is 8 over 18. So it's 1/18, I guess. Yeah, is equal to 1 over 18. And that's the variance. And so that's basically how we solve this problem. So I will pause. I will stop here for this video. And in the next video, we'll look at another example of an arbitrary continuous distribution and kind of how to calculate these things and go from there. So I will see you then.